So I'm going to talk about this boundedness result. Maybe some of you already heard about this in Colorado, but let me remind you. So everything will be over the field of complex numbers. So it's based on 2 papers, and these are the list of authors. So all right. So actually, even though the title is about the minimal model program, there's actually some background behind this. So the very original motivation actually comes from questions about case stability, or more precisely, there is an invariant called local volume for singularities that comes up in case stability. And the original question is, how does this invariant behave in the MMP? And this turns out to be one of the applications that we found. So, but before I get to anything about case stability, or actually I won't mention too much case stability in this talk. Let me first talk about these applications. So as we know, so the minimal model program, usually just called MMP. Right, so in some sense it's a program. So so take some variety of interest, usually with let's say projective variety with mild singularities. So often people consider, let's say, KLT singularities. So we'll see what that means later in the talk. But some mild singularity. And the goal is to so you plug it into this black box. Okay, so maybe I should leave more space from here. So this will be our input. And then so run this so-called MMP, and the goal is to get something that is, for instance, a minimal model of the variety. So it's some nice birational representative of the original one. And so there are some well-understood procedures in this program. So they are usually called divisorial contractions and flips. And so this, the construction exists in general, and the goal is that, so maybe after finding many steps, you arrive at something that's nice. However, maybe one of the big open problem of this field is that, so in order to get to the final output, there has to be only finitely many steps in this sequence. So the conjecture is that actually every MMP terminates in finitely many steps. Or let me just say every MMP terminates. Okay, so let me just write it in full sentence. Terminates after finitely many steps. Right, so so basically at each step of the MMP, so maybe there are many experts in the audience, but so for the non-experts, so there are many steps. So at each step of the MMP, you start to contract curves that has negative intersection with the canonical bundle, and that improves the positivity, and you keep going on until no such contractions are available. And that's what I mean by termination. Right, so, but unfortunately, in general, very little is known. So, so maybe the biggest result along this direction is the work by so BCHM, Burkhardt, Cassini, Haken, McKernan, that says if you start with the varieties of general type, it's a projective variety of general type. KLT of general type. So general type means that the canonical divisor is Q Cartier and big. well, so it's Q-type because of KLT assumption, but let me just say it's big. Then you can run a special sequence of the MMP. And these are called MMP with scaling. So this will terminate. Okay, so that's the general result in any dimension. So for MMP with scaling, that means so at each step there are different choices you can make for the minimal model program. But if you choose the step very, very carefully, then you can achieve termination, at least for varieties of general type. But if you don't choose very carefully, then even in this general type range, we don't know the answer. Okay, so but in particular, but without this scaling, we still don't know termination in general, even for varieties of general type. For general type variety. Okay, so now so there has been some so there are some natural approach that one can try to take, of course. So if you want to show that some sequence like this terminates, then maybe you should come up with some clever choice of invariants that behave well in the minimal model program. And maybe you can show that so this invariant they keep improving, and there are only finite many choices for this, and then eventually you will show the program has to terminate. So that's the ideal situation. And in particular, if this is going to hold, that should tells us that so for most, if you choose some natural invariant, of the variety of varieties only takes finitely many possible values when you run the MMP. Under the MMP. Right? And then, of course, then the goal is to come up with some good choice of invariant in order to control the whole sequence. If this is true, right? So that's an expectation maybe from this conjecture. So let me give you a very concrete example. So one invariant that has been used a lot in the study of the minimal model program is what's called the minimal log discrepancy. So here we call it MLD. All right. So what is this? So now let's just take any variety X, and let's say its canonical divisor is Q cut here. Then okay, maybe I need to switch to a different board. Right. So it's singular in general. So of course I can take the resolution. And then for any prime divisor on the resolution, I can talk about the log discrepancy as usual. So this is the log discrepancy. It's already appeared in Zhuang's talk, for instance. So it's just defined as 1 plus the vanishing, so the multiplicity of the relative canonical divisor. Right. So if I call this map pi. Then I can compare the canonical divisor upstairs and the pullback of the canonical from downstairs, because it's Q-Cartier. right? So then you get the multiplicity plus 1. That's the log discrepancy. And by the way, so I didn't define, I'm sure many of you knows this, but KLT is just the same as saying that this log discrepancy is always positive for any prime divisor. So for any divisor over my original x. Okay, so for any prime divisors on the log resolution. Okay, so now, so what's the minimal log discrepancy? So if I fix a point on my x, then the minimal log discrepancy at this chosen point is just defined as the smallest log discrepancy that you get as you vary divisor. If you look at divisors whose center is this chosen point x. Okay, so it's just the minimum of this log discrepancy such that the center of E is x. Okay, so that's just the definition. And so the reason we care about this is that if you start with your variety x and you run the MMP, then the log discrepancy of individual divisors will be non-decreasing in the whole sequence of the MMP. So so that's why, in particular, right? So if you start with KLT, then it's always positive. So it stays KLT, and so this gives some control on the singularity in general. Yes, the small x. Yeah. So I fixed my point x. Right. So yeah, sure, you can do that. Yeah. I mean, all the interesting informations are contained in the close point already. But yeah. Okay, so all right, so that's just the definition. But maybe what makes this so important is because so Shokroff had shown that if you understand this invariant fairly well, then you do get termination in all cases. Okay, so the summary of statement is that if this minimal log discrepancy invariant satisfy two properties. So the first one is called lower semi-continuity. And the second one is called the ACC, so ascending trend condition. So, which means every ascending trend has to stabilize after finding many steps. Then termination holds. Okay, so then every MMP terminates. Okay, so that's one known approach to this termination conjecture. And actually, more precisely, what Shokroff has shown is the following result. So let me just say theorem. So let's suppose we are given a sequence of the MMP. So let me call this x0, x1, and you continue. It could be an infinite sequence a priori. If the following two statement holds. Okay, so the first one is so for any fixed I can look at the following function. So I take a point on this xi, and I compute the minimal log discrepancy at this chosen point. Let me just label it as small xi. And I want this function to be lower semi-continuous in the Zariski topology, of course, on this varieties that show up in the sequence. And secondly, if I just put together all the possible values of minimal log discrepancy that shows up, so as I vary the points and the variety, so I put together this set. For all I, and I want this set to satisfy the ACC. So there are no infinite sequence that's increasing in this set. Then the conclusion is that this MMP would terminate. Okay, so that's the precise version of Shawcroft's statement of the theorem that he shows. Okay, so in other words, if you want to know termination, so there are these two steps in some sense. So the first application I want to tell you. So this is joined with so maybe with Jingjun Han and Lu Qi. Says that, so let me call this theorem A, maybe. It says so at least that the second part is true for general type MMP. So if X is a varieties of general type, KMT, of course, of general type, then the following set, so let me just call it Y. So you start with your variety X, and you run all possible sequence of MMP starting from that. Some partial sequence of KX MMP. Right, so maybe I should call it some sequence of steps of such an MMP, and you take all possible close points on this intermediate model. Then this set is not just ACC, but actually finite. Okay, so depending on no matter which direction you choose. So in particular. This means that at least for varieties of general type, the termination only is reduced to this low mesometric continuity condition. So in particular, for general type variety, the lower summit continuity of this minimal log disturbancy invariant implies the termination. So I don't know if you have been to this talk in Colorado and you still remember most of this, and you feel a little bit bored in the rest of the talk. Maybe you can try to think about this a little bit. Hopefully that will keep you busy for the next half an hour. So, all right. So let me pull this up. So can you repeat that again? Sorry? Yeah. Sorry. Yeah.
So why does finiteness
imply which one? The so if the set is finite, then it has to satisfy the ACC condition because there are no infinite. Oh, so which? So here I'm considering all possible sequence of the MM. Y is not fixed. Okay. Yeah. So for any, yeah. So anyway, so that's one possible approach. Another approach to this termination, which was taken up in BCHM, is by certain boundedness results, so or maybe finiteness of models in their setting. So the general statement that we can prove at this point which let me just list it as a proposition. So that's in the same paper with Han and Qi, says that so now again, similar to Shawcroft's theorem. So let's start with a fixed sequence of MMP first. Let's assume that somehow this models that appears in this sequence, so there might be infinitely many of them, but if you can show that somehow all these models belong to a bounded family, so in other words, they can be parameterized by finite many components of the Hilbert scheme, so to speak. Then the sequence also terminates. Right. So so in particular, one thing that you have to rule out is if you start with x and you run the MMP to get something called x prime, for instance. Then x prime cannot be isomorphic to x, right? Because, well, otherwise you replace x prime with x and run the same sequence of MMP. There are only finite many models that appear in the sequence, but you won't get termination. So there's, for instance, one thing that has to be ruled out. Okay, so in some sense, in BCHM, they prove, in some sense, this condition, but assuming X is of general type. And in the scaling, sorry? When you say assume Xi belongs to a bounded family, you mean each of them? So all the Xi, when you put together this whole set, all belong to a bounded family. To the same one. Yeah. This one, no, yeah. This one holds in general. Yeah. Actually, I would love to know so if there's like a, so this, so at least for instance, this in particular part, it sounds like there might be some, maybe more elementary approach to this, but strangely, we don't have one, so maybe I won't expand this too much, but let me just remark that it's enough to do it from certain I, right? Yeah, sure. You can always truncate the sequence from the beginning after a few steps. So maybe the one remark, the only remark I would say about this proposition is that so somehow the proof actually uses these stringy Haus numbers. And I'm not sure if there is like a more direct approach to this at the moment. Yes. So basically, no, yeah. After finding many steps, there are no more steps. So that's the way to put it. Okay. So all right. So then if you take this kind of approach, so in some sense, if you compare this with the one using the minimal log discrepancy, the difference is that so if you bound the varieties that appear in this whole sequence, in some sense you are bounding all possible invariants, right? So the difference is that if you can have control of more invariants than just the minimal log discrepancy, then maybe you can avoid this subtle lower semi-continuity property. So that's the message. But still, if we don't know which invariant is the best one, then maybe you just bound everything together. So that's the message from this proposition. All right, so now from this perspective, maybe you want to show some boundedness. And so unfortunately, we can't get boundedness at the moment, but we do get something that's a bit weaker. And it's interesting to see whether this is good enough, and we don't know. But let me tell you the statement. So instead of bounding the varieties that appear in the sequence of this genotype MMP, so again, I start with X, which is the varieties of genotype. Then, so to put it simply, so the fibers of all, let's say, okay, let me call it extremal contractions. I'll explain this with very quickly, or extremal contractions. And all flips in any possible MMP that start with X belong to a bounded family. So in other words, we can't control the entire variety X. But at each step, you are doing some kind of surgery, remove certain locus, and you glue back a different one. So the statement is that the things that you remove and glue, at least if you just take the fibers, those are bounded. So that's the statement. So in some sense, the difference is bounded instead of the individual ones. So maybe the more precise version is that, and where I'm going to introduce these words to you as well. More precisely, right? So it's similar to over there. So okay. So what is this whole fibers business? So start with X. You can run this MMP from X. Maybe after finding many steps, you get to another model Y. And then from there, you have several options to continue the MMP. So you can first take a contraction of some curve that has negative intersection number with the canonical divisor. Some extremal ray, maybe I should say. Right, so let me call this F. So that's a typical procedure in the MMP. So this is the extremal contraction. Sometimes this is a small contraction, and if you want to continue with the MMP, you have to also do the flip. So let me call this Y plus to Z. So this is the flip. When this one is small, so when the dimension, codimension of the exceptional locus is at least 2. Right, so the statement is that you consider every possible options like this, and you take a point inside this space of the contraction, and then I can look at the fiber of this. So a priori disk will give you a very complicated set of varieties, and the conclusion is that this is a bounded set. So there are finding many components of the Hilbert scheme, such that every fiber that appears like this will be parameterized by those components of the Hilbert scheme. And So, okay, so it depends on what kind of generalities you would like for running the MMP. So usually people run the MMP with Q factorial varieties, but there are also ways to run the MMP without the Q factorial condition. So I'm not making that distinction. Yeah. But the statement is going to hold in any setting. So. Yeah, for this proposition, yes.
So if you have a sequence with, is it enough to bound the stringy host numbers, or do you need to bound other numbers?
No, so for this one, just have to bound the stringy host numbers. But the stringy host numbers can go to, it can be very negative, basically. So you don't have like a control on the actual range. So that's also why the conclusion is weaker. All right. So anyway, so we have this. So it's a little bit embarrassing that we still don't know how to use these results to get something that's concrete enough for the MMP. So one application I could mention, and this will be in low dimension, and it's joined with Jingjun Han, Qihao Liu. Is that so maybe if I call that theorem B, this theorem C. So at least we can show that so if X has dimension 5 and is of general type, then so actually it's a little bit stronger than this. So then you can actually find some integer n only depending on x. Such that every MMP starting with this guy terminates in at most n steps. Okay, so but unfortunately that's as much as we can get. So this one is not so explicit. I'll give some remarks shortly, then you'll see. So now let me make a couple of remarks about what I have mentioned so far. So maybe the first remark is a little bit for the expert. Is that so far I mentioned everything for varieties of general type. But if you are familiar with the BCHM, you would know that so actually those MMP with scaling also holds in a slightly general setting. So and that's also true for this theorem ABC. So the theorems ABC also hold. So basically for pairs of log general type, for KLT pairs, such that so either this log canonical divisor is big, or just the boundary is big. Actually, the second one is the main case because everything else is implied by this. Okay, so this is the same. So basically the same setting as in BCHM. Okay, but I just state everything for general type for simplicity. Maybe the second remark about this effective termination is that so okay, so maybe the second remark I should say is that so here we say dimension 5. So dimension 3 and 4, those are known. So in dimension 3, so basically the termination result was proven by Kawamata and Shortcroft. So this is for theorem C. And then if the dimension is 4, then so pretty much it follows from Burkhart's work that you also have termination. So actually in dimension 3, they proved termination for any MMP. And in dimension 4, Burkhardt proved MMP when the codal dimension is at least 0. So in particular, that includes varieties of general type. And in dimension 5, that's the best we can get right now. Okay, and actually in this case, so in these two cases, we also get effective termination. And unlike the case in dimension 5, so here we really don't have an explicit control on this number. But in dimension 3 and 4, we can do a little bit better. So the actual numbers are in terms of basically some topological invariants and volumes of divisors that you can compute very explicitly in terms of a log resolution, of course. But maybe I won't get too much into that. Yeah? Oh, I mean, definitely no. Yeah, definitely no. It's like some, just give you some idea. There's some factorials, big factorials, and some powers in it. So yeah, we didn't try to get any optimal bound in any sense. Okay, so that's the second remark. And the third remark is that, so actually there are a little bit extra information that I didn't state earlier. So there is also an index bound, which is actually the most crucial in this application. So the index bound says that, so let me again assume for simplicity that X is of general type. Then the statement says that so you can find some integer, let me call it R this time, positive integer, such that so whenever you run this MMP starting from X to get some intermediate model, and for any weight divisor on Y that's Q Cartier, the Cartier index is actually at most R, or maybe put it another way, R times L is Cartier. So actually, if you think about this, this would imply that So the minimal log discrepancy is always a rational number, and the denominator will depend on this Cartier index. So in particular, if you have a uniform bound on the denominator, that would mean that this number is at least discrete. Okay? But the original theorem A also claims that it's not just discrete, but also finite. So there's an upper bound as well. Okay, so maybe these are the remarks I want to make at the moment. What do you mean by different numbers of steps? So?
You have this bound, right?
Yeah?
But so other examples when the number of steps are different for two different.
I'm sure they are, yeah. I can give an example maybe later, but maybe not on top of my head right now, yeah. All right, so now maybe I want to say something about the proof. And as I mentioned to you, the proof really uses an invariant that comes from K stability. So this invariant is called the local volume, which was introduced by Shirley a little bit like 10 years ago. So right, so let me first tell you the definition. So now let me fix my X, which is some variety with KLT singularity and also a closed point. So let me just call this a KLT singularity. So at least that would be my notation for a singularity. Okay, so there are different ways to define this local volume. So the original definition, so the notation is volume hat. The original definition is through the space of valuations over this singularity. I'll write down the definition, but this one doesn't matter so much for this talk. I'll give you a second definition that's maybe simpler to comprehend. So the original definition is the following infimum. As you vary over valuations of the function field of x. Maybe let me switch to a different chalk. With center x. And then for any valuation, one can compute, so we can define the log discrepancy of the valuation as well, just like we can define log discrepancy of divisors. And then you raise that to the power n, so n is dimension. And there is also an invariant called the volume of the valuation. And you normalize that by the nth power of the log discrepancy, take the infimum. That's the original definition. I'm not going to elaborate this definition very much. Let me give you an alternative definition that's maybe more familiar to a lot of you. So this definition is due to Yuchen Liu. So you can also compute this as the following infimum. You take n primary ideals. Then compute the log canonical threshold of this ideal, raise the nth power, multiplied by the multiplicity of this ideal, and take the infimum. Okay, so on. And so it turns out that this is a very, very useful invariant. And
are you having to assume that x plus delta is effective when delta is big, or do you also allow the non-effective case?
which part are you talking about?
Remark, you say that A, B, and C hold
For
KLT pairs.
when kx plus delta is big or when delta is big?
If delta is big, do you have to assume kx plus delta is effective, or
No.
Okay.
Yeah. So it's exactly the same as species. Okay, so now let me tell you what's great about this invariant, at least some properties of this invariant. Maybe I should first give you an example very quickly. So if you have work on birational superrigidity or something like that, you probably have seen this invariant at some point. See, so if x is just a smooth point, then it was proven by quality in dimension 2, and then Stephanie, Ein, and Mustafa in higher dimension that this normalized multiplicity is always at least n to the n. And actually, if you plug in the maximal ideal, it's exactly n to the n. Okay. With equality, when you take the maximal ideal, so in this case, multiplicity is 1, and the log canonical threshold is n. Okay, so in particular, the local volume of a smooth point is n to the n. So this is proved using toric degeneration arguments. So actually, you can use the same method to compute this number for many toric examples. I'm not going to do that here. So at least I'm going to convince you that it's quite computable, actually. But maybe the more important things to us are some properties of this invariant. And so this guy has been studied a lot in the context of K-stability. And by now, I think we understand a lot about this guy. So without going too much into a lot of these technical details, let me give you one statement that we can prove in terms of this invariant. So this was originally known as the stable degeneration conjecture. Which is now a theorem due to several people swapped together. So Harold Bloom, Shirley, Chiang Xu, maybe Xiaowei Wang, and myself. That so maybe the easiest way to put this is the following. So every KLT singularity has a local volume preserving I'm really afraid that I'm short of space here. Let me see. Isotrivial degeneration. Actually, a degeneration by test configuration, if you know what that means. But otherwise, just take isotrivial degeneration to okay, I'm clearly running out of space. Right, so to a uniquely determined continue over here. To a uniquely determined so-called K-polystable Farnow cone singularity. So that's the statement. Okay, so I'm not going to define what this whole phrase means. It turns out to be equivalent to the existence of a Ritchie flat Kähler-Kohn metric on the singularity. So there are some canonical metrics that you can put on this space metric. Okay, so that's a lot of information actually behind this sentence. But maybe the message to take is that so in some sense using this local volume one can construct a certain kind of in some sense like an algebraic version of the Ritchie flow. And so you get this canonical degeneration and the final outcome is unique. And more or less, and moreover, in this process, the local volume is preserved. So in some sense, if you understand what's this polystable Farnow cone singularities, then everything else, like arbitrary KLT singularities, can be obtained by doing this isotrivial deform, maybe some sort of deformation, basically. Okay, so so that's a very general statement, but there are some very concrete consequences of this. So one of the consequence, which was obtained by Zhuang and myself at some point, is that so using this local volume, we can actually control, for instance, the index of divisors. So and this boils down to this so-called finite degree formula. So if I have any, let's say a quasi-atomorphism between singularities, between the germs of KLT singularities, then you can actually compare the local volume from downstairs and upstairs. So then the local volume of Y is actually the local volume of X times the local degree of these maps between the germs, right? So this essentially boils down to this uniqueness. Okay, so uniqueness at the end of the day tells you that in order to compute this type of infimum, you only have to look at, for instance, Galois invariant ideals, and so those ideals descend, and that's how you compare the degree. So this uses the uniqueness part of this stable degeneration. Okay, so I'm running a little short of time, so maybe I won't go into a lot of details. And the reason this gives you this index bound is because in particular, that tells you that so for instance, the local fundamental group of a chaotic singularity will be bounded from above by this number, so n to the n divided by the local volume of the singularity. And by the way, I didn't say this, but this local volume is always positive, so that's Shirley's result. And the reason is that if you pass to the universal cover, that's also a chaotic singularity, and the local volume of the universal cover is given by this number times the local volume of downstairs. But so this local volume has some semi-continuity behavior. So basically, if you so word singularities will get smaller volume. So so n to the n is the largest volume you can get, which is the volume of a smooth point. Everything else would be smaller than that. So in particular, it cannot be bigger than this number. So that means you get this inequality, right? So so in particular, well, so if you have some weight divisor, then the index is always at most the size of the local fundamental group. So this gives you the index bound, okay, which is the discreteness of the minimal log discrepancy. I'm a little bit short of time, so let me just mention it very quickly. What about the boundedness? So that relies on another result that Zhuang and I proved maybe last year. So it says that if you fix the local volume, and consider the set of k polystable Farnow-Kohn singularities, whose local volume is at least some fixed epsilon, positive, then this set is bounded. And let me remind you that, so in general, chaotic singularities, even if you fix the local volume, cannot be a bounded family. Because if you have a non-isolated singularity, hypersurface singularity, for instance, there could be an infinite dimensional deformation space. However, for this Farnow-Kohn singularities, you do get boundedness. And that's quite special. And so the consequence of this is that and the consequence of this is that, so if you can bound the local volume from below by some constant, then you can also control the minimal dot discrepancy from above by some fixed constant, depending only on this epsilon. Okay, so basically you have to make use of this bounded family in a different way. So basically the real content of it is for theorem A. So the finiteness of the minimal log discrepancy is that so if you start with the varieties of general type, then there exists some number, positive number, such that for any MMP and any closed point inside X prime, the local volume of this closed point is at least epsilon. Okay, so there's some uniform bound throughout the MMP. So the problem is that in general this local volume does not have any monotonicity inside the MMP. So the way we get around this is by introducing a global invariant that somehow compares well with this local version, which is called the log canonical volume. So let me just define it very quickly. So in the general context, if you have a pair x comma d and this d is big, so define the log canonical volume. Let me use capital letters of x delta. Is defined as, so we replace this boundary by a linear system. this is a linear system of this boundary, such that so for every member in this linear system, scaled appropriately, stays, let's say, KLT. In the n, the degree n part of the linear system. So because it's big, this number is positive. So basically, the proof is by showing that, so first of all, the local volume of singularities is always bounded from below by this, this global version, the log canonical volume. And this guy is monotone. So it's non-decreasing. In the MMP, and if you start with something of general type, then at the beginning it's positive. So then this guy stays positive in the end. I'm sorry, I think I'm a little bit way over time, so maybe I'll just stop here. But I'm happy to take questions.